Alright, this video we're going to continue finding domain algebraically, but this time we're going to talk about finding the domain after we've done some function operations. So these notes are function, singular, function operations, and domain. Alright. So just in case you have forgotten, we've got typically four operations that we're used to. So we're the sum, the difference, the product, and the quotient. Those are kind of the four that we're used to normally. And the notation for function operations is usually where students tend to struggle. So the sum notation that messes with students' minds is if it says f plus g of x and it's written like that, and that really just means you're taking f of x and g of x and adding them together, because there is no such thing as just plain old f and plain old g. The difference, f minus g of x, is really the same as just taking f of x and subtracting g of x off the end. You might write a note to yourself on this one, is that when you write the second function that you're subtracting, you need to put parentheses around the whole function so you can distribute the negatives. That's something that students mess up a lot, so watch for that. Product would be like f times g of x, and again we are just multiplying f of x and g of x together. Typically this is going to involve some foiling, so that might be something to write. You should put parentheses around all of f of x and all of g of x, then you would be foiling those together. And then the quotient is f divided by g of x, which is the same as putting f of x on the top and g of x on the bottom. Alright, and then the last operation that we do with functions is composition, which you should have seen before. And this, sometimes people write fog. And what that means is you're taking the g of x and you're plugging it into f of x. So this would be f of g of x. So it means that you took one function, and anytime you saw an x in the other function, you'd put it in for that x every single time you saw it. That's what that means. Okay, so we're going to do a few examples of this. So first example, we have f of x is defined as the square root of 2x plus 1. And g of x is defined as x to the third minus 5. And when I'm doing these types of problems, before I even get started, I know we're about to have something where they're going to tell us to add or subtract or multiply these. Before I even get started, it's kind of helpful to find the domain of these original pieces, because they will help us find the domain of the whole thing later on. So here, if we remember our rule, we can't have a negative underneath that radical. So I know this is going to be greater than or equal to 0. So 2x is greater than or equal to negative 1. And if I divide it by 2, I get x is greater than or equal to negative 1/2. So I'm going to keep that in mind as I work with this. Over here we have a cubic function, and those, there's no limitation there. We don't have a radical, we don't have a rational to look out for. So all real numbers is what I've got going on there. Okay, so now we're going to start off doing an example of finding the sum of these. So we're just going to say we need to do f of x plus g of x. And that means that what we are writing is the square root of 2x plus 1 plus x to the third minus 5. So as far as f of x plus g of x goes, this is our answer. We can't combine like terms, that's totally done. Now, if we're doing a second part here where they're asking us for the domain of this, then we have to consider the domain of these two different parts. So for this part right here, it says we can use any number that we want, but for this part, we're only allowed to have x values that are greater than or equal to negative 1/2. So think with me for a second. If you were like planning a dinner party for your friends, and you had one person that was gluten-free, this is like the gluten-free person, and then everyone else can eat whatever you make, then your overall meal is probably going to be gluten-free, because you just want to make the same thing that like works for everyone. So when we look at domains, whichever domain happens to be the most limited is what the final answer is going to be. It's what you would be serving at your math dinner party. So x is greater than or equal to negative 1/2 is one way to write it, or you could say negative 1/2 to infinity. Alright, so whenever you do this, you always go with the most limited domain. Alright, let's say we were doing the quotient, and let's say we're taking g of x and dividing it by f of x. So here, g of x is x to the third minus 5, and then f of x is the square root of 2x plus 1. Alright, so there is, I've done the function operation there, so that's an answer. But now I have to consider what my domain here should be. So I know that because I'm including these two things, I have all real numbers, and it has to be greater than or equal to negative 1/2. So I know that that is part of my domain. But now I need to look at my answer and see if there's anything about my answer that should limit the domain even further. And if you look, you have your radical on the bottom of a fraction, which means that you cannot equal 0 on the bottom of a fraction. So instead of saying that 2x plus 1 was greater than or equal to 0, which is what we did when we found our domain up here, we really should get rid of this equal to part and just say 2x plus 1 is greater than 0. So if we're going with the most limited domain, then we're going to say x is greater than and not or equal to, it can't equal to, negative 1/2. So here we're going to say negative 1/2 to infinity. Alright. Another example, we're going to have some different functions here just to keep it interesting. So I'm going to say h of x equals x minus 3. And I'm going to say k of x is 1 over x plus 1. Okay. So again, I'm going to see what the domain of the original functions are. So this is a linear function, so that's all real numbers. And here we have a rational function, and I know that x cannot equal negative 1. So I'm going to keep that in mind as I do this problem. Alright, so the first one we're going to find here is we're going to do the difference. And I'm going to have us do h of x take away k of x. So that means we're going to do x minus 3, and we are subtracting 1 over x plus 1. And this might be bringing back all sorts of terrible memories, because if you're thinking it through, we can combine these. We just have to get a common denominator. So currently this is over a 1. And so I'm going to multiply it by x plus 1 on the top and x plus 1 on the bottom to get that common denominator. So for this first fraction, I have a denominator of x plus 1. And I'm foiling the top, right? So I've got x times x is x squared. X times negative 3 is negative 3x. 1 times x is 1x. So that makes negative 2x when I combine those. And then 1 times negative 3 is negative 3. And then I'm subtracting off 1 over x plus 1. And so I can go ahead and make that into one fraction. So I've got x squared minus 2x. I had a negative 3, I'm subtracting another 1, so now I've got negative 4 over x plus 1. So there, I have finished the function operation, but now I need to find the domain. So the domain is my original problem, said all real numbers here, but over here it said I can't equal negative 1. So I know I'm going to keep that in mind as this answer, so I can't equal negative 1. And now I'm looking at my final answer to see if my domain should be any more limited than I already have it. And there's nothing here that tells me I should have it more limited than just skipping negative 1. So I'm going to go ahead and say that's what the domain is. So all real numbers, but x cannot equal negative 1. And so we have negative infinity to negative 1, and negative 1 to positive infinity. And one thing to be careful of, students when they write the domain, sometimes they will not put the all real numbers part, they will just say that x cannot equal negative 1, which is technically not accurate because your definition of a domain is the possible x values. So if you're just saying x equals negative 1, then you're not saying what's possible, you're just saying what you can't have. So really we need to have the all real numbers there to be thorough. Okay, so we're going to do another problem with those same original functions. So here we're going to do the product. So we're going to do h of x multiplied by k of x. And our h of x was x minus 3. And our k of x is 1 over x plus 1. And we're multiplying those together. And so this is kind of a nice problem. If you guys remember how to multiply these, you just multiply straight across. So we have x minus 3 on the top and x plus 1 on the bottom. So we have performed the whole operation there. And now for our domain, we just have to consider skipping -1. So we're ignoring -1, but aside from that, do we need to limit it any further? And the answer is no. So this domain is exactly the same as the one that we just did. So all real numbers, x cannot equal -1, or if we're doing the other notation, we're writing it like that. There we go. Okay. And then one last one, of course, we have to do composition. So here's our very last example. So we're going to say we have w of x is x squared plus 1, and z of x is the square root of x minus 1. And so if I think about my domain of this original function, this domain would be all real numbers. We can include everything there. And then over here we've got x minus 1 should be greater than or equal to 0, which means x should be greater than or equal to 1. Alright, so I'm going to go ahead and have us do, this is composition. And I'm going to have us do it both ways. So first, let's go ahead and do w of z of x. So this means that we're taking z and we're plugging it into w. So w was x squared plus 1, so I'm going to say I have something squared plus 1. And then the thing that I'm plugging in is z. So it's the square root of x minus 1. Alright. Now, where students mess up is they typically will find their answer, they'll simplify this, they'll get to the end, and then they'll look at the end to find their domain, and it will throw everything off. So I'm going to go ahead and have us do the domain right now so that we can compare it to the end and see what we would have thought otherwise. So if you look at this problem, we know that all real numbers was right here, and we know over here we had to have only numbers that were greater than or equal to 1. So if I look at the function right now, I'm seeing like, yeah, that stuff still fits. I don't see a fraction in there. There's nothing more that's going to limit it that way. So I'm going to say it looks like my domain is greater than or equal to 1. So now let's continue working on the problem and see what happens. We've got a square root and a squared, and those are canceling out. So we just have x minus 1, and then there's the plus 1 on the end. The minus 1 and the plus 1 cancel out. We just get x. So when we did that composition, we got x. A lot of students would look at this problem and say, oh, the domain is all real numbers, because they're just looking at the final answer. And so you have to be careful of that, because the domain is not all real numbers. It's x is greater than or equal to 1. And these are kind of cool. I know I didn't check my answers on any of the other ones, but these ones are kind of cool to see if you plug it in the way that you solved it, like the way that you originally composed the problem. You'll actually be able to see that it's only going to graph the part where x is greater than or equal to 1. So that's a good way you can go back and check these if you have a calculator with you on that part to make sure you're doing it correctly. Okay, and then we're actually going to do the other composition as well. So, and I'm going to do the other forms you guys can see. They would be like Z-O-W, ZOW. And what this actually means is just take W and plug it into Z. So if you don't like that notation, you could change it. That's really what that means. So this time we're starting off with z, so we're going to do something minus 1, and the thing that we're plugging in for x would be x squared plus 1. Okay. So here, if I am considering this one, we're going to simplify this. So I have a plus 1 here and a minus 1 here. So I've got the square root of x squared. And then the square root and the x squared cancel. I just get plain old x. So this one, also equals x at the end. And now something that I did not do a very good job stressing on the first part of this, is that when you do composition, the part of the domain that is especially limiting on composition is the domain of the function that ends up on the inside. So here we're going to write this as a note off to the side. Pay special attention to the domain of the inside function. And the reason for that is that I know that of these two domains, this one was all real numbers and this was x is greater than or equal to 1, so we would kind of assume that the domain of this should be x is greater than or equal to 1, but it's not, because if you consider what you have just plugged in here, if we're looking at this original one right here, this is an x squared, right? And if you plug any number into an x squared, that's always going to be positive. So we have a number that's always positive here, and then we have these two numbers, the +1 and -1, that are going to cancel each other out, which means we are always taking the square root of a positive number. And so this domain is actually all real numbers, which might be kind of surprising, considering what we had noticed the pattern to be throughout all of these notes was that we typically could just look at the domain of the original and get more limited. But this one, depending on what your inside function is, may not actually do that. So again, if you are confused on that, we can check it. So I'm plugging in the function as it looked when I composed them. So x squared plus 1 minus 1. And if you graph that, you can see it made an absolute value function. You can see that all of the x values are included. There's nothing missing there. And so that fits our domain of all real numbers. So the most important part of this is to pay special attention to the inside function. We're just looking at the inside function, and that is different from all of the other function operations that you would do.